head speaks a language I don't understand. I just wanna feel real love, feel the home that I live in. 'Cause I got too much life running through my veins, going to waste. But I ain't keen on living either. Before I fall in love, I'm preparing to leave. I scare myself to death. That's why I keep on running. Before I've arrived, I can see myself coming. I just wanna feel real love, feel the home that I live in. 'Cause I got too much life running through my veins, going to waste. I don't know how to stay close. Wherever we go, it feels like home. Let's go. And the minds and songs. And I know these days will carry on. If we hang and fight asleep to the break of dawn. Oh,
Hi everyone. Welcome back from the lunch to this tutorial session on SRv6 that's going to be presented by Jakub Horn from Cisco. Jakub?
Hey everyone. Hey, good afternoon. Welcome to SRv6 Introduction session. I'm SRv6 TME in Cisco, and I want to do some introduction to SRv6. So I'll start with why we started with SRv6. Basically, this is how typical service provider network looks like today, right? It's very split into the different domains. There is a traditionally layer 2 VPNs in an access. There is a layer 3 VPN over MPLS in a core, and there is a VXLAN in a data center. And that's difficult. Every single service you need to build for your customers, you need to actually build in 3 different domains where are totally different technologies. So you need different expertise, different teams, different everything. On top of that, you need to build the stitching between the domains, right? So from layer 2 VPN to layer 3 VPN, you need to the wirehead end. VXLAN and MPLS, you need some DCI device. These devices, these stitching points are typically very complex to build, and they have issues with the scalability, they have issues with anything. It's really difficult. So what we are trying to achieve with segment routing is really build technology end to end, right? from all the way from the cell site router all the way to the Tor in a data center. And this is generic approach of segment routing. You really want to simplify the network. And then if you build a service, in this example, you have only two touch points. One touch point is the Tor or in the data center, and second touch point is basically cell site router. And you will build any service like this. It's super simple, super easy, and simplicity is main objective of SR. With SRv6, we want to extend that concept even further. We foresee the need to start the service on the G node B, so in the software, in a G node B on the cell side, going all the way to the host in a data center. And then network becomes some very simple construct providing essentially just IPv6 routing with maybe some SRv6 extensions. And this is the main motivation. We really want to entirely simplify overly complex networks as they are built today. We want to build something much simpler, and we want to preserve all the good values of the network. So we want to preserve traffic engineering, fast convergence, but we want to make it much simpler than the industry build all the MPO things over the last 20-25 years. So I will try to guide you through such a transition. So I will start with the technology itself. I will start with the data plane. I'll show you how the data plane in SRv6 is built. What does it mean to build the data plane, how the data plane looks like, how we construct traffic engineering, and how we optimize traffic engineering. Then I'll do what we call SRv6 network programming, which is kind of like a language. It's like the giving meaning to the sits, and you will see what is it and how we are using that and how it is standardized. And then obviously I'll go through two topics which are super important for service providers. One is the data plane, one is the IGP protocol, and second is BGP protocol, right? IGP for underlay, which is very typical, very common in service providers, and the BGP for overlay for services, layer 2 VPN, layer 3 VPN, whatsoever. So let's start with the data plane. Any packet in SRv6 network is IPv6, nothing else. SRv6 is essentially just IPv6 on steroids. It's just a little improved IPv6, nothing more. And that's the beauty, because it brings the simplicity, right? We go back to the root of the simple routing, simple summarization, simple scaling. So every single packet in SRv6 network is IPv6 packet. Most important field in a IPv6 header is obviously destination address. And in SRv6, we play with destination address a lot. We are changing destination address on the path, and we are giving destination address field different meaning, different semantics, different logic. And we will go through that. But that's basically the only thing we are doing differently in SRv6. We are just giving different meaning, different semantics to destination IP address of every single packet in SRv6 network. Second most important field in IPv6 header is next hop. Sorry, not next hop. Next header. Next header is the second most important field, and it's the field which was renamed from the protocol. In the past, in IPv4, it was called protocol, and it was always delineating which protocol is in IPv6 packet. So in this example, 6 means basically TCP. So if I have next header 6, it means the protocol I'm encapsulating is actually TCP. But also from day one, I can encapsulate into the IPv6 packet another IPv6 packet or IPv4 packet, like in this example. So I can take any IPv4 packet and I can encapsulate it into the IPv6 packet and just use 4 as an next header, which says, okay, that the encapsulated packet is IPv4. Same way, I can encapsulate layer 2 frames. I can simply take layer 2 frame as a service for any customer, and I can encapsulate it into the IPv6 packet and transport it over routed network end to end, wherever both ends are terminated, right? important concept in SRv6 or in IPv6 actually is header chaining, and that was basically the reason why they changed the name from the protocol to next header. Because suddenly the protocol was only one, and it was only one thing encapsulated in IPv4 packet. But with IPv6, you can put multiple headers within the multiple function, right? So, for example, you have IPv6 header, then you encapsulate into the IPv6 header, you encapsulate authentication header, and the IPv6 header has a next header 51, which means authentication header, and then you encapsulate TCP, which is 6. Or you can again encapsulate IPv4, which is 4. Anything you can do. And that concept is super important, and we use it sometimes in SRv6. Because there is one additional header which is part of the segment routing, which allows us to do traffic engineering with SRv6. And it's called routing header. And again, routing header is part of IPv6 protocol since day one. It's really 20 years old thing. And it was defined like in the beginning of 2000, or basically end of 90s. There were, over the years, there were different types, different routing header types defined in IETF. So there was a routing, source routing, Nimrod. Type 2 is for mobility. RPL, I don't even have a clue what is it used for. And in segment routing, we put new routing header type, and that's number 4. This is route header type 4, and it means segment routing. Segment routing header, SRH. And the thing is, we put into the SRH list of SIDs, segments ID. We want to make sure the packet is passing through, right? So SID is always 128 bits. We put different SIDs in, let's say, kind of reverse order into the SRH. So if I say reverse order, it actually means the first SID is furthest down in the SRH. It's like at the bottom. It's far away from IPv6 header, and the last SID is very close to header. And unlike in MPLS, we have different concept of moving along those SIDs, right? So we don't pop them. So we have pointers in a header. So there is a well, kind of less important field, which is called last entry. And last entry is actually pointer to the last SID in a SID list. Well, last SID actually means first SID, the first SID which will be used on the routing path. Then there is another field which is called segments left. I don't like that name because it doesn't say anything. I would rather call it active segment. Active segment would be a much more appropriate name for the segments left field in a routing header, because that segments left field points to what we call active segment. So from that list of the SIDs, only one SID is currently active, right? And well, active segments left pointer points to the active SID segment, and the active SID segment is always copied to outer IPv6 header, right? So SID, I use the term SID several times here. SID is short for segment ID. Segment ID looks like IPv6 address, but it is not IPv6 address. It doesn't have any protocol stack connected. Well, if there is an IP address, there is always IP protocol, IP stack behind, so you can telnet it, you can send HTTP packets there, you can SSH it, whatever. There is IP stack in the software behind the IPv6 address. SID is something different. It's segment ID. It looks same because it's 128 bits long, and it has certain structure. Well, I said already it has different semantics, but let's start with the structure. It has at least 2 portions, and we will dig a little bit more into the detail in the SID structure. But here, let's say we have just 2 portions. we have locator, and that's certain number of most significant bits. On this example, you have 64, but it can be basically anything. And locator is the part of the SID which is exactly like IPv6 address. It's routable portion. As a portion, every device in SRv6 network will advertise into the routing protocol. So everyone who's participating in a SRv6 network knows how to reach my locator if I'm the device which is capable of doing SRv6. So I need to advertise it into the routing table. And the function is actually what I'm gonna do with the packet. So it defines what I want to do, what I can do, which kind of service I can offer to everyone to use on myself. We'll go there a little bit more in a minute, but let's use this split for now. So try to imagine there is a device, there is a source device which wants to send the packet through other devices. There is just packet for some intent, for some reason. I want to send the packet through router 1, router 2, router 3, and terminate it on router 4. And now, obviously, those routers are not in a shortest path in SPF, right? They are anywhere. They can be anywhere routed. And I said every device in a SRv6 network is basically advertising locator into the routing protocol. So everyone here, sorry, everyone here actually is having the routing information to get to any /64. And if I'll say routing information, it doesn't mean literally everyone has in his routing table /60/64, right? They can have summary of 60/64. So they can have /48 summary of some domain if it's router, or they can have /32 to some network. Or if it's the host, and we said the SRv6 is possible on the host, it can have just the default routes to everywhere. It just have a reachability to everywhere. And that's big difference compared to any MPLS. Also, well, I said in the beginning, I work for Cisco, so router for me is like the main thing. But the device which understands SRv6 or providing SRv6 functionality doesn't have to be a router. It can be anything else. It can be firewall, right? Firewall will provide firewalling function, and the source, for some reason, wants to send the packet through the firewall. Well, firewall will advertise the locator, and me as a source, I can always use that firewall anywhere in the network. It can be a data center in a different country. It can be in a AWS or Google Cloud. It can be anywhere because just I have routing information to get there. Right, so it doesn't have to be router. It can be basically anything. And right now I'm the source. I want to make sure, for whatever reason, I have intent to send this packet through those 3 routers or any device. I want to terminate it on the destination device, which is router or any device for. And also, I will say that those devices on the path, they don't have to be physical devices, right? It can be virtual machine, it can be container, it can be host, it can be anything which is reachable, anything you can assign the locator to it, anything capable of doing SRv6 function. So right now, if I'm the source, I need to build the packet to make sure that the packet or content is going through all those 3 devices terminated on 4. So I need to build the SID list. And I said that, so I'll build the SID list in kind of the reverse order. So SID number 1 is at the bottom of the SRH. SID number 2, and so on and so forth. And indexes are from top to bottom, 0, 1, 2, 3. And because I'm on the first hop, I'm originator of the packet, I want to make sure the packet goes first to the router 1. So I will set segments left, which I would rather call active segments pointer, to 3. So it points to very first segment in the SID list. And this SID, because it's active SID, is actually copied to the destination address field of outer IPv6 header, right? Which is right here. Right now, I build the packet. Everything is in the packet. Packet is entirely built. Well, And what I'm supposed to do, I will send it out. Where? Well, it's based on a destination address, right? If I'm the host and I have just default route, I will send it this direction. If I'm the router, I will just use my routing table and send it over the shortest path towards the destination. And between me and the first router or R1, there can be multiple other devices. There can be other routers. It's different to MPLS. Those devices, this device here in the middle, it's not SRv6 capable, doesn't have to be. Only function I need there is basically just simple IPv6 routing, because I'm not expecting anything else than IPv6 routing, right? So I'll send a packet. This device, which is not the destination, which is small router, legacy old crap, which is able to do only IPv6 routing, will take the packet, take a look into the destination IP address and forward it based on the destination IP address. He's not supposed to do any lookup what is inside. He's not expected to inspect whether there is a TCP or UDP or SRH on that matter, right? He will just do simple IPv6 forward, which any router is capable of, right? And between me as the source and the R1, there can be multiple different legacy routers or whatever routers. I need just IPv6 connectivity. That's the only thing I need. So the packet will get to the R1, which is in case is a router, but we said already it can be firewall, it can be any appliance or any virtual thing. Once it gets to the R1 is supposed to do 3 simple steps, very simple steps. So first step is to decrement segments left. Segments left pointer is decremented by 1. So new segments left is 2. That's the first step. Well, if segments left, what I would rather call active segment is 2, it means new active segment is the one with the segment with the index 2, right? So what I'm gonna do, second step is obviously to copy active segment to the destination address. So right now, active segment is in a destination address. And the third step is simple. I will just forward it towards the new destination. I have new destination address. I have the routing table because locator of router 2 is advertised everywhere in the network. I will forward it because I'm in the middle of network. My routing table more likely will be a little bit more complex, but still routing table. I have some form of route to 2001 DB8 002/64. Maybe summary, maybe /64, maybe just a default. Doesn't really matter. I will just forward it there. And again, between R1 and R2, there can be any legacy device, right? I need just IPv6 routing reachability between R1 and R2. Nothing else. They don't have to understand SRv6 at all. It's just plain simple IPv6 routing all the way to the R2. R2 will do 3 things. Well, simple. Decrement segments left, copy new active segment to the destination address. So new destination address becomes the router 3 and forward according to this routing table. Again, between 2 and 3, whatever is there. Maybe between 2 and 3, there is even router 1, or maybe there is a router 4. Doesn't matter. They are supposed to do only plain simple IPv6 routing, nothing else. And this way, router 3 is supposed to do still those 3 simple steps. So decrement segments left, copy new active segment to the destination address and forward accordingly. But right now, router 3 is a little bit smarter, right? Well, he realizes the new segments left, so new active segment pointer is actually 0, which means there are no more possible sits in the SRH. So he's smart. He wanna just save MTU, save the overhead on that network between R3 and R4, and we'll just remove SRH. We call that PSP. It's optional. It's optional. It's not always the case. By default, our routers, well, most of the routers from most of the vendors are doing that, but it's optional. You can decide. You can preserve SRH. Obviously, it's good to get rid of that, but there might be reasons to keep that. Example of such a reason would be let's say router 4 wants to be sure he will accept only packets which went through firewall. And one of the sits in a sit list is the firewall. So by checking that, router 4 can verify this packet is secure, and I can accept it because it went through the firewall, right? And that's it. That's SRv6. SRv6 is just IPv6 routing. Let's take a look a little bit more at that sit. We said there is a sit, it has certain structure. We split that structure into the locator, which are the most significant bits, and it's part which is really like IPv6 address. It's a routable portion of the sit and has all the properties of IPv6 address. Routable, it's aggregatable, it's everything. And then there is a function. Function is what I'm gonna do with the packet. I will inspect the packet, whatever. I said, well, in the previous example, we had the locator size 64. And this is here, like 64, but it's not. It doesn't have to be like that. It can be anything. It can be 80 bits. It can be 81 bits. It can be 79 bits. Doesn't matter. It can be even shorter. It can be 48 bits. Same with the function. Function doesn't have to be 64. It can be 80, like in this example, but it's very hard to imagine a device which would do 2 to the power 80 different functions. So it's more likely it will be something smaller, like 32 bits or maybe even 16 bits. And at the end, because there is nothing to share, I don't need anything else. Well, my function is just 32 bits in this example. So I have the padding, and padding is just zeros, just all the zeros. I don't care. I don't have any use for that information. It's just redundant. We can split locator further to the locator block and node ID. And the function we can split in a function itself and an argument. Argument like the argument in the programming language, right? In the programming language, you have the function and argument, or sets of arguments, and you're passing that to the function. Example of the function and argument. Function on the device, which is SRv6 capable, and I'm providing QoS service to everyone, right? QoS service, you can use me for QoS service, and I'm offering 2 functions. Function 1 would be policing, function 2 would be shaping, right? An argument would be size of that shaper. So if you send me the packet on the function 1 with the argument 10 gig, I will just do the policing to 10 gig for all those packet sends to this address. If you send me on function 2 with the argument 20 gig, I will do shaping for 20 gigs. That's just an example. I'm not saying we are having that function an argument, but it goes beyond just the networking, right? The function can be storage drive, because, well, that SRv6 capable device can be really the storage, network attached storage. And the function can be access to the specific storage device, and the argument can be cluster on the device or the sector on the device. That's possible. We are already doing some research in this area. Or the function can be the specific video stream, and the argument can be timestamp in that video stream, right? So I can encode any information into the function and argument. In most cases, for most production networks, we are not using arguments, or there is only one exception, and that exception is ESI filtering in EVPN. That's only place where we are right now using in production code the argument. Okay, TSID next, microSID. The concept I just introduced has one disadvantage. The disadvantage, it builds quite large packets, right? So I'm building the packet and I want to send it through 5 different devices, like on this picture. And those devices, again, we said it can be routers. I have some intent to send the packet through some different path, or it can be virtual machines or containers. But most likely they are coming from my network, right? So the beginning of every seed is coming from same range. Well, I will do the logical address assignment. I will assign certain part of my address space. I will assign to all the seeds in my network, all the locators. So the beginning of every packet is actually the same, right? That's the kind of natural and it's very common in today's deployment. End of each seed is that padding I mentioned, right? All the zeros. But still, I'm encapsulating everything. I'm putting that redundant information into the packet actually 6 times. So 5 times in SRH, once in outer IPv6 header, and I'm putting there a lot of redundant information. This causing basically unnecessary overhead, right? I'm just utilizing my links too much because I'm putting there a lot of information, and the packet overhead is bigger, which is obviously an issue. And also, the legacy hardware has issue to create such an encapsulation, right? The legacy hardware wasn't designed to build the long headers. They are optimized to build small headers very efficiently on very fast speed. So what we are introducing is the microSID. microSID is SID, but it's small. Well, as the name said, here the ITF uses the term CSID, which is compressed SID. Still, industry using microSID significantly more, and that microSID can be something smaller than 128 bits. In that full SID, every full SID means 128 bits, but I want to use something smaller. So here in this example, we are using 16 bits, and our implementation is exactly 16 bits. And others vendors implementation is exactly 16 bits as well. And I can put multiple microSIDs into what we call SRv6 microSID container. So that container is exactly those 128 bits, just to fit into IPv6 address destination field. So I can put certain number of microSIDs. Again, size can be different than 16 bits, but here in this example is 16 because it's easy to read, easy to understand. And I will prepend it with SRv6 microSID block, which is 32 bits. And again, here it can be anything. Here in this example, it's 32 bits, easy to read, and this is actually again implementation which is used across all the vendors, and basically all the vendors I know testing exactly this format last weekend at the NTC in Berlin. And I can do, and again, that those 16 bits, they have basically same meaning like the full SID, right? I don't need for all the information, I don't need always 128 bits. So I'm using just the 16 bits. And this way, I can encode exactly the same path, like in the packet on the top. I can encode the same information with just IPv6 header, because I will put into the destination address the container with the 5 different microSIDs instead of 5 full SIDs here. And this packet, they will achieve exactly the same. There is no difference whatsoever. They will achieve exactly the same. We just need the microSID support. Well, how does it work, right? We had an example with 4 different routers. We have headend, which is the source, and we have a couple of midpoints, so router 1, router 2, router 3. And again, they don't have to be routers, they can be firewalls, virtual, physical, containers, whatever you like. And we want to for sure preserve that capability of simple plain IPv6 routing, right? We don't want to have every router capable. So source right now is not going to build any SRH. It can eventually, but not now. He will just take the SRv6 microSID block, first 32 bits, because every single device here is advertising this locator, and right now, because the SRv6 microSID block is 32 bits and the node ID is 16 bits, every locator is actually 48 bits. Everyone is advertising those 48 bits. So the headend will put first 32 bits, which are common across all the locators and all the SIDs, into the container, and then he will put one microSID after another. And this way, he will build the packet and he will send it out. And right now, you see the beginning of the packet is 2001 DBA:1, which is advertised by router 1. So he will just send it out. And based on a routing table, and again, routing table can be summarized, can be full table, can be just a default route from the host. If this is the case, well, just the packet will send towards the router 1. And again, right now, it goes through router, which is legacy 1, right? This guy doesn't understand any SRv6 microsignal or any SRv6. This is still old plain IPv6 router, which can do just IPv6 routing, nothing else. So he will send it, and obviously this router will do just plain IPv6 routing. He will forward packet based on a destination address, and packet will get to the router 1. Not eventually, well, it should, because there is a routing information. And router 1 right now doesn't need to do all 3 steps. It will do just 2 simple steps, and we call them shift and forward. So he will shift whatever is beyond the locator block. He will shift it by 16 bits. This way, he will get new IP address, new destination IP address, and forward is just the forwarding based on a new destination address, right? So we'll do just shift and forward. Right now, shift by 16 bits. This way, again, between R1 and R2, there are multiple different routers. Maybe legacy, maybe they don't understand SRv6. But what they have to understand is IPv6 routing, nothing else. They will deliver the packet to router 2. Router 2 will do the same thing, shift and forward. With this shift and forward, it will change the IP address and will forward towards the router 3. Router 3 will do, again, shift and forward. But right now, he will do a little bit different shift, right? Right now, because he's using some more extensive function, which is denoted like 3, and something after that, maybe some argument is there, maybe some local function, something else is there. So he can use 32 bits, or if needed, he can use 48 bits. Whatever is necessary for that particular function on that device, he can use. So right now, this device is doing the shift not by 16 bits, by 32 bits. And this way, we are getting basically exactly the same packet like in previous example, which is reaching out to our final destination, which is router 4. Does it make sense? Is it reasonable? Questions? Okay, there is a question on the screen. In the previous examples, we had just one container, right? And in a container, if I have 32 bits block and 16 bits the node ID, I can use only up to 6 different node IDs into the one container. What I'm gonna do if I need more than 6, and in this example there is 11 seats, what I'm gonna do? What can I do? Is there any trick, or what would we do? Okay, that's actually simple. I'll split it into 2 containers, right? I will put first 6 microseeds into the first container and remaining 5 into the second container. And when I'm building the packet, I'll put the first container into the destination address right here, and second container into the SRH, like previously, exactly the same thing. It's totally compatible. It's still the same thing. We are not changing anything. We are just being a little bit more efficient on the seats, right? We don't need to do anything else or anything special. And right now we will do forwarding, and on the right hand, and on the right hand side, you have a list of the routers or any devices I want to send the packet through. So I will send it because destination address is there. I will send it to the router 1. Router 1 will do shift and forward. Router 2 will do shift and forward. Router 3 will do shift and forward. Router 4 shift and forward. Router 5 shift and forward. And right now I'm getting to router 6. Well, the router 6 has the special value where it sees there is no additional microseed, there is just 0, which actually means, I didn't mention that on previous slide, it's end of the container. End of the container means the packet is either for me or there is another container somewhere in SRH. And in this case, there is another container in SRH. So what he's going to do? Simple as before. So he will do 3 steps. Decrement segments left. So segments left becomes 0. copy new active segment or new active container to the destination address and forward it. Copy and forward. Right now, again, he's smart. He sees the segment's left pointer is 0. So I want to be optimal with MTU. I want to be optimal. I want to help egress PE to handle the packet, not forcing him to do large decapsulation. So I'll just remove the SRH, which is called PSP, and it will send it towards the new destination. And new destination is router 7, shift and forward, 8, shift and forward, 9, shift and forward, 10 and 11 is our final destination, right? And this way we can do, well, maybe 16 SID, maybe 30 microSIDs, doesn't really matter. We can do anything. You notice I used different things, right? In that container, sometimes I had just 16 bits microSID, or sometimes I use 32 bits, like 2 microSIDs, one after another. Well, there are reasons for this, right? That the first 16 bits, they have to be always globally unique. And we call them, they are coming from GIB, Global ID Block. And these are the part which is always assigned to the router. So if we are one single network here, and every one of us is the router, every one of us will have different GIB. So I will have 1, 2, 3, 4, 5, 6, all the way to DFFF. I can use that part of those 16 bits for the GIB. And the lib is local. So every one of us has local portion to assign to local functions. And it's only locally significant, right? So every one of us will use probably E00 for maybe adjacent SID or for the service SID and so on and so forth. These are reusable. They are locally specific. And that's important. If you want to do traffic engineering, I need to know whether it's for me or whether it's for someone else. Okay, let me do a quick time check. Okay. There is another field in IPv6 which is super important and super cool in terms of SRv6, and it's called flow label. Flow label is only field which was introduced as a new field compared to IPv4 in IPv6, right? It's only new field in IPv6, and it's used for entropy. It's used to encode the entropy. Well, historically in MPLS, entropy was disaster. The originally MPLS didn't have any entropy encoding. So over the years, the FET pseudovar label was introduced, entropy label was introduced. The different devices were handling that differently. With SR introduction, it was difficult to decide where this entropy label will be located. That was difficult. That was disaster, and industry never really settled this in a good way. In IPv6, we had a solution day one. It was prepared for us, and it's called flow label, which was meant to be IPv6 header to encode entropy. So what we are gonna do if you are encapsulating, if I'm ingress PE in SRv6 network, I will just get the packet, I'll do the hash always for load balancing purposes. And this time, on top of that, I'll take that hash, that 5-tuple hash, which is the standard thing, and I will encode that 5-tuple hash into the flow label. So I have 20 bits, and always encode the flow identification, so 5-tuple hash, I will encode into the flow label if I'm ingress PE. And the midpoints, well, any PE or basically anything is mandated to use that flow label for his 5-tuple or for his hash calculation, right? So this way, this PE, well, different flow will end up with different flow label, and the P, which is in the middle, will do the hash, including the flow label. So despite those two flows in SRv6, once they are IPv6 encapsulated, they seem to be like identical flows. They are not. They are different, and only validation is that flow label. And if that P2 in this picture doesn't do the flow label doesn't put the flow label into the hash calculation, those flows would end up on the same link, right? And there will be issue. And this is nice and beautiful solution for encoding entropy, which didn't exist in MPLS at all. Okay, it's good. Network programming. Network programming sounds very scientific, but network programming is actually only thing what we are trying to express the change semantics of the SIDs. In MPLS, everything is just a label, right? Everything is just a label. But well, over years, well, everyone is using term overlay label, underlay label, service label, IGP label, LDP label, BGP label. There are different terms used. They are not very standardized. But essentially, it's just a label. And what we try to do day one in SRv6 to give the SIDs the meaning, like you can name them. Or just it has some meaning. You have the name, you will describe that. We built a whole RFC on top of that, well, not on top of that, just to describe all those different functions. And what we try to do to use, well, to create the function, specific function, to create basic MPLS network functionality. So let's start from the most basic SID name, which is called end. End actually means end of the segment. And it's the simplest one you can imagine. It's just really the end of the segment and doesn't have any other meaning. You don't do anything else. So there are different flavors. There are plenty of them. But actually the meaning is the decrement segments left, copy active SID, and forward. There are different names. There are PSP, USP. I'm not going to go into the details. Important, well, this is really end of the segment, but the same set is always end with next. And this is what I've described, right? The next actually means shift and forward on top of decrement segments left, copy active SID, and forward it, right? This is default endpoint. It's called end, and it's end of the segment. And this is that example with the end with next, right? Oh, well, it will do decrement segments left, copy new active SID, and forward. In a case, I do have end of the container, but in general, most of the cases it's doing just shift and forward, which is just end of the segment, or nothing else. And apparently, it's like same thing, like the node SID in the SRMPLS, right? It has same functionality. Node SID in SRMPLS is basically termination of the segment. It's end of the segment, and there is a shortest path towards the destination to that segment. That's the simplest one. Second one is end.x. And again, end of the segment, and x. It's not the best naming again, but it actually means cross-connect. It means specific interface. So if in the name there is an end.x, it means send this packet to the specific interface. You don't care what is the destination IP address. So in destination IP address, and in this example, your destination address, you will do shift. So you will do shift and forward, right? You will shift by 32 bits because that end.x is always 32 bits, or 2 times 16 bits. And right now, well, he will do shift. So you will shift by 32 bits. So new destination is 2001 DB84 something, which is advertised by router 4. But right now, the router 3 will not do any lookup into his forwarding table, right? He will just blindly send it to the 10 gigabit 000 because that interface has assigned that adjacency, right? This way, if I'm the head end, I can decide which interface I'm gonna use, whether the one with the low latency or the one with the large latency, or the one which is not utilized over the one which is heavily utilized. If I will do just end function of the router 4, it will go ECMP over those two. This way, I can really select which one I'm gonna use. So this is end.x with next. Then there is a family of functions. Okay, I didn't say that. It's the same thing, like in MPLS is an adjacency set, right? That we sometimes call it UA, microset with A adjacency. Simple as that. Then there is a set of the defined functions, which are with D and X, right? X, you know what it means. But there is a D, and D means decapsulate. Decapsulate means whatever is encapsulated inside, and there are three different flavors or three different behaviors. And there is DX4, which says, well, decapsulate the IPv4 packet which is inside. There is a DX6, which means decapsulate IPv6 packet which is inside, or DX2, which means decapsulate layer 2 frame which is inside. Here is an example of DX4, because encapsulate is IPv4 packet. This function has to be always last function in a set list, right? Because I'm decapsulating. I'm throwing away everything what is there. And if it's not last set in a function, I will discard the packet immediately. So this is always and last set, and always results in a decapsulation and sending to the specific interface. Does it remind you anything from MPLS world? Any click? Is there some equivalent in MPLS? Yeah, there is. There is basically, if you do per CE label allocation or per prefix label allocation, it's exactly the same behavior, right? So it's exactly the same behavior. You just do the lookup on the label and send it to the specific interface. Same here. You will just do the lookup on the SID, and if it matches the NDX4 function, you will send it to the specific interface. And there is another family which is called DT, and DT4 and DT6. Well, there is introduction definition of DT2 as well, but it's wasn't made public really. But here we are doing the same thing, and T means stable lookup. So I will decapsulate, so it again has to be last set in a set list. I will decapsulate and do T as a table lookup. So I can pick any table in the router 4 here where the lookup is done. So it's same thing like per verb table lookup, per verb label allocation, or deaggregate label in an MPLS. It's exactly the same thing. It just have different name because it's not just a label, right? And basically, that RFC, that SRv6 network programming, is the set of the different functions with the different names, and they are always very well defined with the pseudocode, what it has to do, and what is it for, right? I didn't cover all of them. There are some which are for as a binding seats, binding seat for traffic engineering policy. There are a couple of them for layer 2 services, couple of them for layer 3 services, and couple of them for the global policies. Right, and this is important, and it's also important for service providers, right? You will put into your RFP, we need support of and DT6 function, and everyone knows what does it mean. It's just a single sentence, and everyone will understand because it's perfectly defined in RFC, and everyone has to comply with the pseudocode which is in that RFC. Okay, questions? No questions? Okay. So I'll go for signaling, right? Signaling, well, so far we covered entire data plane, right? And entire data plane means everything in SRv6 is just IPv6. Only thing in a data plane we are changing is basically semantics of the IP address, and we don't call it IP address anymore, we call it a SID. But we're just trying to make sure everything is the same like in MPLS, just simpler. And well, obviously we need to say what is advertised in which protocol and which way. So the certain SIDs, certain functions are advertised just in IGP, which is kind of logical, right? I don't need to advertise the end function, end of the segment in the BGP for service. It doesn't make any sense. And certain things are defined for service, for BGP only. So for example, end DX4, I will never advertise in IGP because IGP is IPv6 only, and this is obviously v4 related. So this one will be always advertised in a BGP. Everything is meant to be advertised in BGPLS. BGPLS will grab everything from the network and will advertise it with some Uber controller which controls all the network. So it needs to have all the information about everything in there. But it's not that important right now. What is more important, and maybe I should make it bigger, the locator is not the function, right? It's the locator. That's that part of the SID which is routable portion of that SID. And that SID is always advertised into the routing table, right? Into the routing table. Or in most cases in service provider environment, it's going to be IGP. In the web providers, it's going to be rather BGP. But it's just the routing. That's just routing part. So here we will cover IGP. And IGP, it's interesting, right? And then a while ago on this slide, I always had this implementation for SIS and OSPA will follow. But it seems, well, I don't know whether OSPA will really follow at all. The reason is simple. If you're a service provider having ISIS, you will just search, you will just add address family to do your ISIS, and you're fine. You will just start doing SRv6, right, in your network. That's simple. If you're running OSPF, you're running OSPF v2, right? OSPF v2 doesn't support any IPv6 routing. So you need to start another totally different protocol, which is OSPF v3. And if you want to start another protocol, isn't it better to start ISIS for v3 already? Because it's kind of simpler and everyone else is using. So we don't have any demand for OSPF v3 SRv6 extensions. It is defined at ITF, but don't see any deployment in neither in enterprise or service providers using OSPF v3. So I remove that statement, but right now it's ISIS only. So ISIS uses link states packets, right? Link states packets, it's typical information about the router. So me as a router, by default, I'm advertising the ESI, my address, I'm advertising which interfaces are part of the IGP, I'm typically advertising my host name. When I build that adjacency, I will start advertising my neighbors. So to allow everyone to build the topology and do the Dijkstra. And I'm advertising IP addresses. Whatever network is attached to me, I will advertise it as an attached network. Well, there is typically more to ISIS, but this is the just basic information I'm obliged to advertise to make it work. Well, most of the implementations, they're advertising more than that. So for SRv6, I need to advertise a few more things. Well, first of all, I already said that. There is a locator. Locator, I need to advertise to everyone know how to attract traffic, right? Everyone needs to know this is my locator, and every SID which I'm advertising is reachable here. Then I need to advertise the node SID, UN function, end function, and this can be used for traffic engineering or for TLFA. And same with UA functions, with adjacency SID. So in IGP, I'm advertising end function and end.x function. And both of those, I'm always advertising with the structure. Right? If I advertise the structure, I'm letting you know what I can do. I can do shift and forward. This is, well, size of the block. This is size of the node. This is size of the function. And this is size of the arguments in the SID. So we are giving really meaning of that SID. And we are advertising that for both, for UN and for UAs. You see, here for UN, the function length is always 0. For UA, function length is always 16. So I'm using either just one microSID or two microSIDs from GIP and LIP. And this is okay. On top of that, I'm advertising what we call capabilities. On the which point, I need to advertise how many SIDs I can remove, how many SIDs I can add. I can encapsulate, decapsulate. So there is a set of function which we call capabilities, what the chip or what the device is capable to do. just to allow to do the traffic engineering to everyone else. And this is Cisco example. Well, this doesn't have to be Cisco, right? This is just a Cisco output, but it can be basically from any router, from any vendor. And I can show from other vendors. So you see, I'm advertising locator actually twice, right? Here as a locator TLV, and here as a attached network. Why I'm doing that? Why I'm so inefficient advertising in a control protocol certain things more than once? Why is that? Any idea? No? Well, of course, I'm advertising a SRv6 locator as a locator TLV with certain properties. So I'm letting know to those who understand the SRv6, okay, this is locator, and you can do certain things with the locator. Maybe you can assign the algorithm. Maybe you can do more things with the locator. But we said we want to allow legacy routers to forward, right? Legacy routers, they wouldn't understand any SRv6 locator at all. Only thing they would understand would be attached prefix. And if in the network there is some legacy routers which are not capable of doing SRv6, they need to understand, they need to forward the traffic to me. So I'm kind of doing the trick, advertising the locator as an attached network as well. Same like any other attached network. Then I'm advertising the UN functions and per each interface and the end.x function per each interface in IGP. Okay, that's for IGP, and that's it, right? Let's go to BGP. Let's go to BGP and let's build simple layer 3 VPN rather quickly. Layer 3 VPN, I want to do that same way like before. Everything has to work like it worked with MPLS. So what I'm going to do, in this example, any prefix I will receive from the CE, I will allocate the function. And that function can be, in this example, is UDT4 or NDT4. So that particular function will be per verb. So I have 10 different verbs, and I will assign 10 different NDT4 functions. Then I'm starting receiving prefixes from the CE routers, and I need to advertise them via route reflector to the ingress PE, which is router 1 here, right? And what I'm going to do? Well, I still want to use BGP VPN v4 address family, same like before. So AFI1, SAFI 128. I'm still preserving all the parameters which are part of that AFI, SAFI, VPN v4 address family. So there is always route distinguisher. There is always set of route targets, whatever you say, whatever you configure on your router. Everything is the same. Like with MPLS, there is only one exception. I'm putting on top of that SIT TLV, and that's it. That's all the things I'm gonna do. I will just, this prefix, which belongs to verb 1 or whatever verb, when I'm advertising that towards the SRv6 network, I will just add UDT function, I will just advertise full SIT to that. Full SIT, full 128 bits, with the structure, with everything. I will just advertise it. And well, through the route reflector or whatever, maybe so through the complex routing structure, I will receive that on the ingress PE. Ingress PE will put into his forwarding table the information in this particular verb when I'm importing based on the route target. The address 10.10.22/24 is reachable over FCBD:BB00:3:E002, right? He will put it there, and obviously then he will advertise to connected PE the same prefix in that verb. Well, simple as that. Obviously, I need to locate reachability, right? So between 1 and 3, 1 knows how to reach the locator of 3. It's an IGP, it's part of the IGP protocol or part of the routing, right? Whatever routing is in between. And it doesn't say here, well, that the 1 needs to know locator /48. It doesn't. It needs just the routing information. It can have a summary. This can be super large network, and in between there is some ADR which is doing the summary. Well, this can be huge network, there is some BGP routing in between, doesn't matter. He doesn't need to have /48. He doesn't need to have, like in MPLS, /32 to every single router to communicate. He can have just one single summary to every router there. If this is cell-site router, he will have just one single link to the network. He can have just default route to everyone, right? And that's enough. He doesn't need to have underlay route for every single loopback in the network. And then when he receives the packet from the CE towards the destination, he will do simple stuff. He will just take that packet and he will encapsulate it where the destination address is and DT4 function of the egress PE. And that's it, right? Through the network, which is IPv6 only, the devices that they don't need to understand SRv6. The packet gets routed based on a destination IP address based on the first 48 bits of the destination IPv6 address. It will get forwarded to the router 3. And router 3 will do what it's supposed to do, right? And end of the segments, D, decapsulate, T, table lookup of the inner packet, and we'll send it out to the egress CE. Super simple, extremely scalable. It's basically unlimited scalability, right? Your scalability depends only on BGP. IGP doesn't influence that scalability. You don't need to do any BGP. You don't need to do any complex thing. It's just simple routing with the summarization. Simple as that. And it's the same thing for layer 2, right? So you can do EVPN with layer 2. You can advertise EVI in EVPN with the SIT. It's the same thing. And then the forwarding ingress PE, instead of encapsulating IPv4 packet, is using layer 2 frame, encapsulates it into the layer 3 IPv6 packet, and will forward it through the network, whatever size of the network is. Okay, that's good. That's better. So, migration. Questions? Any questions? Sure. You need a mic. I will probably hear you without that.
Yeah, the question about layer 2 services.
Mm-hmm.
So when we build, for example, EVPN around that, does it have, it doesn't need any VXLAN or anything big, right?
Actually, I don't like VXLAN, right? VXLAN is a useless encapsulation.
Yeah,
you're just
asking about the tunnels.
Yeah. It's just different tunneling, and you're basically encoding that intelligence into the SIT itself, right? SIT already has that information, and you can do everything there. Well, you can do VXLAN over IPv6,
no need.
but you don't want to do that because this is additional overhead, and VXLAN historically is just layer 2. So you are preserving all the layer 2 encapsulation all the time, every time. Here you can decide either layer 2 encapsulation if you want to send the frame, and or layer 3 encapsulation like EVPN around type 5, right?
So we can have just SRv6 unaware network.
Absolutely. Only those
we can have layer 2 domains inside what's separated by BNIs.
Absolutely.
Plus layer 3.
Basically, there is one Asian provider who is using exactly this, and they are going even further, right? They have large data centers across Asia, and they even without our assistance, they realize that if they do SRv6, it's going to be way simpler for them. So they have all the data centers, they are just IPv6 routers, nothing else. All the TORs, IPv6, all the spines, IPv6 only, nothing else. Cheapest devices as possible. And they are doing SRv6 encapsulation from the servers, directly from the servers, and this way they are having the VPN service to service. They are creating, hiding different traffic for different customers. They have like really smart thing to do. And the network is super cheap and everything is programmable. Obviously they are web-like customers, so they are programmers. They are doing everything this way. And it's super easy, super nice, super efficient, and they really love it.
Yeah, and you don't need any MPLS behind that.
No MPLS,
Yeah.
just simple routing. And take a look at the size, right? The size of the network can be infinity. Well, okay, this is one data center with 100,000 servers. Okay, I will just send one single summary to the other data centers. In MPLS, you would be dead like with 100,000, you will be dead immediately. Here, everything can be summarized, everything is aggregatable.
Thank you.
You're welcome. Okay. Migration, and I will cover migration from MPLS. It is perceived to be complex, right? Because we have to change the control plane. So everything in the control plane has to change from the IPv4 to IPv6. we have to change the data plane. So everything from IPv6, from MPLS data plane has to change to SRv6 or ergo to IPv6 data plane. So perception, it is very complex. So I'll try to show you. It is actually simpler than migration from, it's simpler and more granular than migration from LDP MPLS towards the SR MPLS, right? And what we are proposing and what we are doing is what we call dual connected PE. Well, this is your PE. This is typical MPLS PE. And that MPLS PE has some IGP protocol, ISIS in this example. It can be OSPF, and it has some label distribution protocol. And here I'm having LDP because it's still most common, but I don't care if the protocol to distribute labels is OSPF or IGP, like in segment routing. It doesn't change anything. What is important, it has BGP session towards the route reflector. And if I'll say BGP session v4, I mean transport address family. I don't mean whatever is inside, right? It can be VPN v4, VPN v6, EVPN, global table, everything is there. Important, if I'm saying v4, it is from v4 loopback of the PE all the way to the route reflector. It's a v4. It's carrying all the address families you can imagine. And my desired state is actually SRv6 PE. So SRv6 PE is having IGP for v6 only. It doesn't have any v4 IGP. It doesn't need to have. And it has BGP session, which I'm calling here BGP v6. And again, v6 doesn't mean the what I'm transporting. It's transport address family. So it's from v6 loopback to v6 loopback of the route reflector. And obviously here, in my example, I'll use layer 3 VPN v4. So it's advertising VPN v4 address family for simplicity, but it's same valid for all the other address families. And what is dual connected PE is the guy who is having VPN prefixes and advertising that to the both sides, right? To the left, it is advertising everything with a label, and to the right, it's advertising everything with a SID, right? So on the left-hand side, IGP and LDP, and really doesn't matter whether it's just IGP or IGP with LDP, segment routing, no segment routing. So you have loopback reachability and the label assigned to the loopback, right? That's what IGP and LDP is doing. And again, if there is OSPF with segment routing, it's exactly the same. On the right-hand side, from IGP, you need only locator reachability. Locator is only important construct to maintain the reachability. And on the left-hand side, you are sending VPN prefix with a label. On the right-hand side, you are sending same VPN prefix with a SID, right? And I will use this concept to migrate this very simple network. This network is super simple, right? I call them first PE, second PE, and last PE. I have just 3. I don't need more because between there is in your network probably a few thousand PEs, which you will have to migrate some automated way. I have just 1 PE, and you will see I will barely touch the P router or just do the very, very simple thing. Well, obviously in your network, there are a couple of hundreds, maybe a couple of thousand P routers. And I have one single route reflector. In your network, you have at least 2, probably some cluster or some hierarchical structure, doesn't really matter. There is an IGP protocol, v4, there is a label distribution protocol, and again, I'll say it's the wrong term, I just shouldn't use label protocol which distributes the label, because it can be either LDP or IGP, right? Doesn't really matter. I need to have label assigned to any prefix. So I need to do preparation. Preparation means will enable IPv6 routing. So I will enable IGPv6, in our case, ISIS. I will put some loopbacks, still going to be probably loopback 0. I will just add IPv6 address to verify the connectivity. That's simple, right? This way I didn't touch any service. Nothing is touched. Everything is still running over IPv4 and MPLS, nothing touched. Then I will add new set of route reflectors. There is a disclaimer. I can do it with the old set of route reflectors. I can do that. I did that in this network, and this is disaster. This is horrible. This is way to hell. Always, well, I don't know how can I strongly, super strongly recommend always use new set of route reflectors, and you will see why in a minute, or maybe I will explain that in more detail. So we will prepare the V6 route reflectors. They are ready for V6 session. The old route reflectors, they are just V4 sessions. And again, VPN V4 address family, in this case, over V4. And there is DJ, and I wanna migrate first two PEs. Oh, well, I wanna migrate really just one, but to migrate just one means nothing, right? So migrating means I will enable SRv6 on them, so we will start locator advertisement into the IGP. That's the first part, doesn't hurt anyone. Then they will start advertising VPN prefixes towards the V6 route reflector, right? So, well, whatever they have in a particular VPN, they will take it and they will advertise it twice. Once with the label towards the V4 route reflector, once with the SIP to the V6 route reflector. Those route reflectors, well, they are single purpose devices. They will just reflect. They will take those two prefixes, well, each one take the prefixes, and they will send it to the other PE. What other PE is gonna do? Which one is gonna pick? Simple as that. This is just a routing, right? And he will do BGP best path selection because he received two identical prefixes with the same prefix, same route distinguisher, same route targets. Everything is the same. Only difference is the next hop. So he makes comparing the next one, but I'm the smart operator. So what I'm gonna do, I will set the preference towards the V6 route reflector to lower preference than default. So instead of having 100, which is default local preference, I will set here 50. So he received two prefixes, one totally identical, one with a SIT, one with a label. He will compare them and he say, okay, the labeled one is better local preference, so I'll keep in the forwarding labeled one. So nothing have changed, right? All the forwarding is still MPLS. Only thing which I'm checking here is the control plane. Control plane works fine. I'm receiving those prefixes. So what I'm going to do? Now, right now, I can start real migration. And I used to work for advanced services, so I'm very cautious. I don't want to do big steps. I always want to do smallest step possible, right? If I do the small step in this kind of migrations, it has two advantages. Small steps are easy to revert. Well, I will just revert it back if it doesn't work. And on top of that, if I do the small step, it's easy to troubleshoot, right? I will much easier find the issue if there is an issue, and I will just nail it down because if there is an issue in the network, it's very likely connected to that really small step I've done. So, because I want to do smallest step possible, I will just change the local preference of the one single prefix in a one single verb to 150 on the PE1. So, from that moment, he will start advertising over V6 route reflector. He will start advertising the same prefix with a better local preference. So P2 will receive that prefix and will reprogram the FIP. Reprogramming the FIP is the function what P is doing like 1,000 times a day. Well, any router is doing 1,000 times a day. So it's zero packet loss. So he will not lose a single packet. He will just change the forwarding entry from MPLS to SRv6. And from now on, all the traffic from PE2 to PE1 for that one single prefix in one single verb is SRv6 or IPv6 encapsulated. Right? I was cautious, and surprisingly, everything is going to be fine. This is totally working fine. So you will observe that for a couple of days, maybe a week, I don't know, it depends, it's up to you. It's entirely up to you how much you trust the technology, but you will see there is no issue. Everything is there. So you can start with more prefixes, second prefix, third prefix, maybe a whole verb. And you're doing all your migration by just changing the local preference on this BGP session, nothing else. It's simple as that. Super simple to automate, super simple to create. And every single prefix is just routing information change on the other end, and it's really zero packet loss. So you will do that step by step, verb by verb, address family by address family. At a certain point, whole PE1 is migrated, which actually means all the traffic from the PE2 to PE1 is SRv6. All the traffic from PE1 to PE2 is still MPLS, right? I still have that local preference 50 on the PE2. And obviously all the traffic from and to PE3 is still MPLS because it doesn't advertise anything with the SIDs. It doesn't change anything. So this way you migrated PE1 entirely. And then you will go second PE, right? You will migrate it probably a little bit faster because you verify it works just fine. So you will migrate PE2 same day, a little bit faster, probably more automated way. And this way you will migrate all your PEs, right? PE by PE, I don't know, very automated. There is even, well, our big automation view, they're building the automation process there. There are a couple of demos there. It's very simple, very automated, super granular, right? It's much easier. And if you take a look at migration from GP to SRMPLS, it's way from that granularity, right? You always do SR prefer, which means you are switching whole PE at once. So compared to this is kind of the bank, right? You are just changing whole PE. If something is wrong, whole PE is gone, everything is gone, everything is screwed. Here, you do that prefix by prefix, verb by verb, very smooth. And only thing there is just routing. And once I will migrate everything, I'll verify on all the links. I don't see any MPLS packets. I see just IPv6 packets everywhere. And I can switch off everything v4. What was interesting here, I deliberately didn't migrate P, right? I didn't need to, because it's just IPv6 routing. Well, in reality, obviously, I will want to migrate P, because in the future, probably I want to use some traffic engineering through that P or through different Ps. Or I probably want to use TILFA. If I want to use TILFA in my network, it's difficult to do TILFA in this network, but in the real network, there is a lot of TILFA. So I will need to migrate P, but I don't need to do that for services. I only need to do that for the other things which are underlay related. And that's it. That's the way it is. So to kind of conclude, SRv6 is here. It's fully standardized. There is a bunch of RFCs, and we spent a lot of time. I'm not sure whether I kept their Cisco marketing, because we are author of the idea. Actually, it's a person called Clarence Filflis, who is here and having presentation tomorrow here. We are authoring, contributing to every SRv6 draft RFC, and everything is fully standardized. I can assure you all the other vendors are doing the same. I'm every year part of ENTC interoperability testing, which is happening right now. So I was there last week. I'm doing also the SRv6, and every vendor I know is doing SRv6 exactly the same way I described here. And it's very interoperable. Like 3 years ago, we hit a lot of issues, misunderstanding in a control plane, certain things. This year, 0 issues. And actually, even last year, 0 issues, no major issues. SRv6 is widely, not just deployed, this is widely available. Not just with the network equipment manufacturers, there are a lot of merchant silicon providers which supports SRv6 natively in their SDK. And if I say SRv6, I'll always mean the microSID, so CSID next, because I don't think it makes any sense to deploy anything like full SID or any other crazy compression. There is a lot of open source applications which support it. I'm not gonna go through. There is a lot of open source stacks which supports. Actually, Linux supports SRv6 natively from 2016, kernel 4.10, which is like ages old thing. There is SRv6 microSID in a Sonic. There are SmartNIC supporting SRv6. There is everything. There is plenty of deployment. These are just Cisco deployments. Other vendors, they have less deployments, but still they have plenty of deployments. There are a lot of here in Asia. This is very attractive. There are a lot of different deployments, and well, everyone is doing this slightly differently. So that's nice. And if you wanna more information about SRv6, the best source of information is always segmentrouting.net. strongly recommend. There are a lot of demonstrations, a lot of public resources. And if you're anyhow in a CLI, and again, this is the Cisco specific, there is a D Cloud. I built a couple of different labs with the microSIT, so you can do layer 3 VPN with TILFA, with the FlexAlgo. You can do traffic engineering with SRPC, and you can do even the migration I've shown. You can do exactly the same thing and verifying there is really zero packet loss if you're doing the migration. So questions? I don't have anything else. Shoot it. Can we get a mic, please? Or give me the question. I can prepare myself. Sorry, he is coming.
Yes. Coming back to layer 2 services that I had previously. For example, if I want to replace the VPLS instance that I'm running, how does the broadcast or non-unicast works in terms of the SRv6?
We don't have that. We don't have that done. You basically need one single bridge domain. But okay, how it works in a okay, there are two questions. How it works during the migration, or how it works when it's
natively.
Well, it's the same thing. This is EVPN, right? If you remember that those functions, there were specific functions for broadcast and unknown.
Probably I missed that, but
Yeah, that was I didn't cover that in a detail. When I shown the list of the end functions, there were a bunch of them, and at the end there was DTU and DTM. U means unknown, M means the multicast, and this is just EVPN, right? EVPN currently can have 3 data planes. It can have MPLS data plane, it can have VXLAN data plane, it can have SRv6 data plane. And in that sense, the signaling is basically the same. Only what you're advertising either label or VTEP or advertising the SID.
okay, do you know some big implementations of layer 2 services, or mostly it is because for layer 3 it's kind of clear and easy. Layer 2 is more
It's basically the same thing. Most of the service providers I'm working with, they have vast majority of services is layer 3, right? This is the most important. Second service in terms of importance is point-to-point pseudovirus. This is like the second one, and everyone has that. Every SRv6 implementation already have that, and the EVPN ELAN is less deployed, but it's deployed. It's always supported, and since like recent release, we support active. We support basically everything. So I don't know. Every service provider on that list has some form of layer 3 VPN. Most of them they have point-to-point pseudovirus with layer 2 VPN, not on the same scale, but they have, and some of them they have the ELAN as well. So it's every service provider has all the services basically.
Yeah,
and it's not like layer 3 VPN is for vast majority the most important service.
Yeah, exactly. Thank you.
Pleasure. Some more questions? Any more questions? If not, thank you for your time. Thank you for being here. It was a pleasure. And if you have any question, I'll be here for a few more minutes. Thank you very much. Have a nice day.
Too many times did I sit here and cry. After the lies, can we say our goodbyes? Why are you playing? I'm tired of saying you took it all when you walked out on me. Go take it all with you. Moonlight on the morning dew. Romantic advice. Romantic advice. Romantic advice. Moonlight on the morning dew. Romantic advice. Romantic advice. Romantic advice. Romantic advice.